Please, everybody, mute your microphone so that I start now. I start now. Okay. Is it audible?
Yes, sir,
Yes,
it's
sir.
audible.
Okay. Yeah. Good evening, everybody. I'm going to discuss about three-phase circuits. Coming to outline, introduction to single-phase system. Introduction to is introduction to single-phase system, introduction to three-phase system, balanced three-phase system. In that, we are going to discuss star connection, delta connection, phase sequence, as well as line to phase quantities in three-phase circuits, power and three-phase circuits. Okay, today we are going to discuss all these topics. So, coming to the introduction. Actually, we have plenty of applications. Actually, we have plenty of applications of three-phase system. Okay. Actually, we are generating three-phase system, three-phase voltage. Okay. Of course, we are utilizing single-phase voltage. Okay. Here, we can see one of the applications, three-phase electric arc furnace. Actually, what we are going to do is here we are by using three-phase system, we are going to produce electric arc. That arc is being used to heat charged metal. Okay, so for making iron, okay, sorry, for making steel, we can use that heat. This is one of the applications of three-phase system. Okay. So this also works on three-phase system, three-phase source. Okay, three-phase system. We have industrial fans. Okay, most of the industries utilize three-phase system. Actually, domestic appliance need single-phase system, whereas industries need three-phase. Industries, some of the industries need three-phase system. Okay, which plays major role. Three-phase system plays major role. Okay, so if you want to utilize more amount of power, okay, it is possible only by using three-phase system. Okay, if you use single-phase system, more power cannot be utilized. Okay, so here this is one of the applications, industrial fan. Okay, this also works on three-phase system. Okay, here we have a three-phase induction motor. Okay, this also works on three-phase system as it is three-phase induction motor. Okay, this also works on three-phase system. Okay, and one more example. Here we have three-phase generator. Okay, wind power plant. In wind power plant, we use three-phase generator in order to produce three-phase supply. Okay, normally we generate three-phase supply, not single-phase supply. We utilize single-phase supply for domestic appliances, but will not will not generate single-phase supply. Okay, we produce three-phase supply. This is also one of the applications of three-phase supply, three-phase system. Okay, this works on three-phase supply. Coming to traction. Okay, here as we are using three-phase induction motors over here. Okay, these three-phase induction motors require three-phase supply. Okay, so for proper operation, what these motors, I mean, anyhow, for more power rating, as we are using more power rating of motors, okay, we are giving three-phase supply to them. Okay, so we require three-phase supply to induction motors, which we are using in traction motors. Coming to single phase system, so far we have discussed about single phase system. Already we have discussed about single phase system, right? Okay, right? According to the Faraday's laws of electromagnetic induction, generally uh, here we have two poles. Okay, this is one coil. Actually, this is armature winding. Okay, all coils are connected into this. We can make armature winding. Okay, this winding is, okay, we have two poles. Okay, this winding is being rotated inside this magnetic field so that EMF will be produced. Okay, so according to the Faraday's laws of electromagnetic induction, let me explain in brief. Okay, so right, poles. So this is north pole. Okay, whereas this is south pole. Okay, let me place one coil inside of this magnetic field. I'm placing one coin inside this magnetic field. Okay, so if it is placed like this, then you can't collect EMF. Okay, let me place load, R load. Okay, across this. See, this is uh, this is this is one conductor. This is another conductor. Okay, two conductors will constitute one coil. These two conductors will constitute one coil. Okay, uh, this is one conductor, this is another conductor. These two conductors will constitute one coil. Okay, so if you place this coil inside this magnetic field, no EMF will be induced. Okay, until there is time variation between magnetic field and conductor. Okay, so we need to produce time variation between magnetic field and conductor. Okay, actually, see, what are the essential requirements in order to produce EMF? Okay, so first one we require magnetic field, and second one we require conductor, and we need to have time variation between conductor and magnetic field. Okay, so whenever, according to the Faraday's laws of electromagnetic induction, whenever flux in the coil changes, EMF is induced. Okay, so in order to make that happen, okay, what we have to do is we have to rotate this coil. Okay, we have to rotate this coil. Okay, so that when we rotate the coil inside this magnetic field, so that we are creating time variation between magnetic field and coil. Okay, so that EMF will be induced. Okay, so according to the Faraday's laws of electromagnetic
Hello.
induction, whenever flux in the coil changes.
హలో సార్
Hello.
సార్ వాయిస్ ఆడిబుల్ లేదంట సార్, కొంతమంది క్లారిటీ లేదంట. హలో సార్.
Yeah, yeah. Is it okay now? Hello.
ఇప్పుడు బాగానే వినపడుతుంది సార్.
Start question చెప్పనా? Hello.
చెప్పండి సార్.
Question చెప్పనా?
ఏమో సార్, కొంతమంది చాట్ బాక్స్ పెట్టారు కదా సార్, వాయిస్ నాట్ ఆడిబుల్, క్లారిటీ లేదని చెప్తారు మరి.
అవునా? పెట్టలేదా?
ఇట్లేదా? ఒకసారి మీరైతే చెప్పండి సార్, చూద్దాం ఒకసారి.
ఇప్పుడు నీకు వినిపిస్తుందా?
వినిపిస్తుంది సార్ ఇప్పుడు, కానీ అంటే కొద్దిగా స్ట్రక్ అయినట్టు అనిపించింది పాంక.
ఇప్పుడు అక్కడ అనిపిస్తుందా?
ఇప్పుడు కూడా కొద్దిగా స్ట్రక్ అయింది సార్.
అవునా?
సార్ ఇక్కడ నుంచి చెప్పండి సార్. ఎస్ సార్.
ఇప్పుడు వినిపిస్తుందా?
ఇప్పుడు వినిపిస్తుంది సార్.
వినిపిస్తుంది సార్.
Now it is audible, right?
Yeah.
ఎస్ సార్, ఆడబుల్.
I'll raise my voice.
Okay.
Okay, coming to single phase system. Okay, normally here we have two poles. Magnetic field will be produced by these two poles. Okay, here we are placing coil. Actually, it is not coil. We are placing here armature winding. Okay, winding is placed inside this magnetic field. Okay, coming to basic operation of generator. Okay, here this is the north pole, whereas north pole, this is south pole. Okay. Let me place one coil. This is one conductor. This is another conductor. Okay, two conductors will constitute one coil. Okay, this is one coil. Okay, let me, in order to collect voltage across this coil, let me place R load across this. Okay, right. Now, actually, in order to produce EMF, according to the Faraday's laws of electromagnetic induction, in order to produce EMF, in order to generate EMF, okay, we require magnetic field and we require conductors or coils and time variation between magnetic field and conductor. Okay, so if you place this coil inside of this magnetic field, no EMF will be induced. Okay, so according to the Faraday's laws of electromagnetic induction, whenever flux link in the coil changes, EMF is induced. Okay, so in order to have time variation between magnetic field and coil, let me rotate this coil. Okay, so if I rotate this coil inside this magnetic field, EMF will be induced according to the Faraday's laws of electromagnetic induction. Okay, that is, whenever flux linking the coil changes, EMF is induced. Okay, if you rotate this coil, then only flux linking the coil will be changing. Then only EMF will be induced. Okay, otherwise EMF will not be induced. Okay, so in order to make that happen, we have to rotate this coil inside this magnetic field. So there will be time variation between magnetic field and conductor. Okay, so EMF will be induced. Okay, so here, yeah, one more thing. Armature winding means here this is one coil. Actually, this is one conductor. Okay, this is one conductor. This is another conductor. Two conductors will constitute one coil. Okay, so one number of, this is one coil. This is one coil. Okay, this is one coil. This is another coil. Okay, likewise, number of coils are connected in series like this. When number of coils are connected in series like this, okay, then this will be armature winding. Then this will be armature winding. Okay, if you connect number of coils in series like this, okay, you can make armature winding like this. Okay, so here, yeah, okay, so whenever, according to the Faraday's laws of electromagnetic induction, whenever flux linking the coil changes, EMF is induced. So I am rotating armature winding. Okay, so in single phase system, in single phase generator is having only one armature winding. Okay, that armature winding is rotated. Okay, that armature winding is rotated inside of this magnetic field. Then EMF will be induced. Okay, so you're going to have waveform like this. Okay, E is equal to EM sin omega. Okay, that will generate E is equal to, okay, EM sin omega t. EM sin omega t. Where EM is maximum value. You can also have, see, this is equal to, you can also write like this in polar form, Em at an angle 0 degrees. You can also write like this is equal to Em by root 2, Em by root 2 at an angle 0 degrees. Okay, this is the RMS value. Okay, mostly the representation would be like this. Okay, we represent, if you want to represent this voltage, sinusoidal voltage in polar form. Okay, normally we represent this voltage, sinusoidal voltage like this. Okay, RMS value at an angle 0 degree. RMS value at an angle 0 degree. Okay, this will be the voltage which is generated by single phase generator. Okay, okay, it is having only see here the generator producing a single phase supply, and which is having the generator which is having only one armature winding and which will produce single phase supply. Okay, that is sine wave like this. Okay, and which is equal to that induced voltage is equal to Em sin omega. Okay, so when you rotate this coil inside this magnetic field, EMF will be induced according to this Faraday's law of electromagnetic induction. Okay, so you can have this sine wave like this. E is equal to Em sin omega. This is single phase supply. Okay, so in polar form that can be represented like this. Okay, this is single phase supply which will generate only single voltage. Okay, which is having magnitude as well as phase angle. Okay, whereas in case of DC voltage, it is having no phase angle. It is having only magnitude. Okay, so there is no problem of representing DC value directly. That can be represented as magnitude value. Okay, so we don't have any phase angle over there. Okay, whereas in order to represent AC value, okay, there is magnitude as well as phase angle. Okay, that's why we have three forms to represent AC voltage. Okay, what are they? They are RMS value, peak value, and what? Average value, right? Okay, so here this is RMS value. VP is average value. VP is RMS value. RMS value at an angle 5 degrees. Okay, so single phase system consists of generator connected to a pair of wires. Okay, so this is single phase voltage. Okay, that generator voltage can be represented like this: voltage at an angle 5. Okay, this is RMS value, whereas this is phase angle of this. Okay, so this is connected to load. ZL is load. Okay, where VP is what? RMS value. Okay, and phi is phase angle. Okay, so single phase system will generate only single waveform. Okay, as it is having only one armature winding. Okay, so one armature winding will produce only one voltage. Okay, if you have more than one armature winding, means if you have two armature windings. Okay, if you have having two armature windings, if you rotate two armature windings inside of this magnetic field, then we are going to produce two more voltage. Okay, one more voltage means two voltage. Totally two voltage will be produced. Okay, so in case of single phase system, we produce, as we are having only single armature winding, that armature winding will produce only single voltage. Okay, whereas in case of polyphase system means if the generator is arranged to have two or more separate windings, two or more armature windings. Okay, then that system is called polyphase system. Okay, so if the generator is having two armature windings, okay, two armature windings will produce two equal and different voltages, two equal individual voltages. Okay, so we can have that system is called two-phase system. Okay, here we have two-phase system, right? Okay, two-phase system means here we are going to have two phases. Two phases are two armature windings. Those two armature windings going to produce two voltages. Okay, whereas coming to this three-phase system. Okay, anyhow, this is polyphase system as well as this is also polyphase system. This is what three-phase system. Okay, three-phase system is again same as this. It is having three. It is having three armature windings. Okay, as it is having two armature windings. Two armature windings will produce two voltages. Okay, three armature windings will produce three voltages. Three individual voltages. Okay, provided that if we rotate all armature coils instead of this magnetic field, then we are going to produce 3 armature winding voltages. Okay. So coming to two-phase system. Okay. So in case of single-phase system, we have generated only single waveform, that is which is in sinusoidal form. Okay. So here we have two-phase system. Coming to two-phase system. Okay. The generator, coming to what two-phase generator. Two-phase generator will produce two-phase system. Okay, two-phase system. Okay, so a generator which is having 2 armature windings. Okay, the generator which is having 2 armature windings is called two-phase generator. Okay, here this is yeah. Okay, yeah. Here we have 2 armature windings. Here we have only two armature windings. Okay, this is armature winding 1. This is armature winding 2. 2 armature windings. Okay, so this is two-phase generator. This is two-phase generator as it is having 2 armature windings. Okay, if we rotate this these 2 armature windings inside of this magnetic field, and then this will produce 2 voltages. Okay, so here now what we are doing is this is coil 1. A1, A2 is coil 1. Okay, coil 1, or you can say armature winding 1. Okay, coil 1. Okay. This is coil 1, whereas this is coil 2. Okay, this is coil 1. If the coil 1 is placed like this, okay, then we have to place we have to place coil 2 like this. Okay, so there should be phase angle between the phase angle between these two should be 90 degrees. Actually, here this is physical connection. Okay, this is physical connection. Okay, physically these two coils are separated by 90 degrees. Okay, physically they are separated by 90 degrees. Okay, if the coil 1 is placed like this, then coil 2 should be placed like this. Okay, physically the angle between these two should be 90 degrees. Okay, physically they are separated by 90 degrees. Okay, so if we rotate this arrangement having 2 coils, okay, displaced by 90 degrees physically, then 2 EMF will be induced. Okay, those 2 EMFs electrically displaced by an angle 90 degrees. Okay, so here see, you can this. Okay, so these 2 coils are displaced by an angle 90 degrees physically. Physically, they are displaced by an angle 90 degrees. Okay, when you rotate this kind of arrangement instead of this magnetic field, then they are going to produce 2 EMFs. Okay, this is E1, whereas this is E2. If there is 90 degrees displacement physically, automatically there will be 90 degrees displacement electrically. Okay, so electrically these 2 voltages are displaced by an angle 90 degrees. Okay, this is physical arrangement, whereas here electrically they are displaced by an angle 90 degrees. Okay, so we have to displacement between these 2 coils should be 90 degrees physically. Okay, so this is coil 1, whereas this is coil 2. We are displacing this coil is displaced by an angle 90 degrees. Okay, these 2 coils are displaced by an angle 90 degrees, 90 degrees from each other. Okay, then this is the voltage which is produced by coil 1. Okay, that this is the voltage which is produced by the coil 1. Okay, then the voltage from coil 2 starts from here. Okay, this voltage lags this voltage by an angle 90 degrees. there will be electrical displacement. Okay, they are 90 degrees apart from each other. Okay, so if this is the voltage which is produced by coil 1, okay, then the voltage from coil 2 is displaced by an angle 90 degrees from this voltage. Okay, that is uh, this is the zero crossing point of phase A. Okay, this is zero crossing point of phase A voltage. Okay, this is zero crossing point of phase B voltage. Okay, they are displaced by an angle 90 degrees from each other. Okay, so now what will be the voltage? What will be this voltage? What is the voltage produced by coil 1? Okay, that could be let E1 is voltage produced by coil 1, that is equal to E1 is equal to EM sin omega t. If it is EM sin omega t, then what would be E2? E2 is equal to EM sin of omega t minus 90 degrees. EM sin of omega t minus 90 degrees. Okay, that is in polar form. E1 is equal to E at an angle 0 degrees. E1 is equal to E. This is RMS value. E at an angle 0 degrees. Okay, whereas E2 would be E2 is equal to E at an angle minus 90 degrees. Okay, E2 lags. This is E1. This is E2. E2 lags. This is E2. Okay, E2 lags E1 by an angle 90 degrees. Okay, physically they are these two coils are displaced by an angle 90 degrees, as well as electrically they are displaced by an angle 90 degrees. Okay. Okay, so this is all about two-phase system. Okay, that will generate two voltage as it is having two armature windings. Okay, so two voltage, if E1 is equal to Vp at an angle 0 degrees means another voltage would be Vp at an angle minus 90 degrees. Okay, these two voltages are displaced by an angle 90 degrees. Okay, now coming to three-phase system. Okay, three-phase generator will produce three-phase system. Okay, actually we generate three-phase voltage. Okay, three-phase system. Okay, so three-phase generator will produce three-phase system. Okay, three-phase voltage. Okay, now here as it is three-phase system, we are going to have three coils, three armature windings. Okay, so three-phase generator is the generator which is having three armature windings. This is having three armature windings. See, this is armature winding 1, this is armature winding 2, this is armature winding 3. Okay, see, they are displaced by angle 120 degrees from each other. Okay, if this is coil 1, if this is coil 1, okay, then magnetic field, okay, north pole, south pole. This is coil 1. Okay, this is A dash. Okay, then okay, so A dash, A double dash. Okay, then another coil would be like this. Okay, that coil is displaced by an angle 120 degrees from this coil. Okay, so this would be B dash, B double dash. Okay, so the phase angle between these two would be 120 degrees. The phase angle between these two would be 120 degrees. Okay. Similarly, the phase angle between coil B and coil C should be again 120 degrees. So you can draw like this. Okay. This would be C dash and this is C double dash. Okay. So the angle between these two would be 120 degrees. Okay, so here see. Okay. So the angle, see, this is coil A. Coil A. Okay. This is coil B. Okay. The angle between these two is 100 degrees. The angle between coil A and coil B is 100 degrees. The angle between coil B and coil C is again 120 degrees. Again 120 degrees. This angle is 120 degrees. Okay. All armature windings are displaced by angle 120 degrees from each other. Okay, all armature windings are displaced by an angle 120 degrees from each other physically. Okay, if you have this kind of arrangement, obviously we are going to produce three voltages, and that voltage are displaced by an angle 120 degrees from each other electrically. Okay, so this is phase A. Phase A will produce this voltage. Okay, this you can have E1. E1, sorry, let me write here. E1 is equal to EM sin omega t. Let E1 is equal to EM sin omega t. Okay, that is the voltage which is produced by phase A. Okay, then as there is phase difference between coil A and coil B, as there is 120 degrees phase difference between, physical difference between coil A and coil B. Okay, so phase B will produce voltage. That voltage lags E1 by an angle 120 degrees. Okay, so that voltage will start from here. Okay, this is 120 degrees. 120 degrees. Okay, this is 0 degrees. Okay, this voltage will start from 0 degrees, whereas phase B, the voltage which is produced by phase B, starts from 120 degrees. Okay, this lags this. Okay, so you can write, you can write E2. E2 is equal to EM sin of omega t minus 120 degrees. EM sin of omega t minus 120 degrees. Okay. Coming to phase C voltage, the voltage which is produced by phase C. Voltage produced by phase C lags voltage produced by phase B by an angle 120 degrees. Okay, the phase difference between these two would be 120 degrees. Otherwise, we can also say like this: the voltage produced by phase C lags phase A by an angle 240 degrees. 240 degrees. Okay, the voltage between these two would be 120 degrees. Sorry, the phase angle between these two would be 120 degrees. Okay, so you can write E2 is equal to it is difficult to write the EM sin omega. So let me write V RMS value. Let V at an angle minus 240 degrees. 240 degrees. Okay, so here E1 is equal to E at an angle 0 degrees. E2 is equal to E at an angle minus 120 degrees. E3 is equal, sorry, this is E3, right? Sorry. E3 is equal to E at an angle minus 240 degrees. Okay, so all are displaced 120 degrees from each other. Okay, as there is physical displacement of 120 degrees here. Okay, here there is electrical displacement of 120 degrees from each other. Okay. This is the voltage which is produced by coil 1. Okay, coil 1. Okay, and this is the voltage which is produced by coil B or coil 2. This is the voltage which is produced by coil 3. Okay, V at an angle 0 degrees, V at an angle VP, or V at an angle minus 120 degrees, V at an angle minus 240 degrees, or it is equal to V at an angle plus 120 degrees. Okay, you can also write like this. Okay, see here. Uh, Generation of balanced three-phase voltage. Okay, so let me explain in brief. Already got this slide. Okay, so this is coil A. Okay, coil A. Okay, two ends A dash coil A. Okay, this is coil B. Okay, uh, the angle between these two is 120 degrees. Okay, this is coil C. Okay, again this is A dash, right? C. Okay, C means, sorry, yeah, sorry. This is coil A dash. This is coil B. Okay, A B. Okay, this is the starting terminal of coil A. This is the starting terminal of coil B, and they are displaced 120 degrees from each other. Okay, coming to coil C. This is coil C. Okay, the angle between coil A and coil C is again 120 degrees. Okay, all coils are displaced 120 degrees from each other physically. Okay, so the generator basically consists of rotating magnetic field. Okay, yeah, normally as we have discussed earlier. Okay, actually we have rotated coil instead of the magnetic field. Okay, in order to provide time variation between magnetic field and coil. Okay, you can also rotate magnetic field. Okay, instead of rotating coil, here in case of three-phase generator, practically we are not rotating this armature windings. Okay, we are not rotating armature winding. Okay, we are rotating, either you rotate armature winding or you rotate magnetic field. Okay, in order to provide time variation between magnetic field and coil. Okay, so here we are rotating magnetic field. Okay, here rotor itself is producing magnetic field. Okay, when it gets excited, okay, magnetic field will be produced. Okay, if it is stationary, anyhow coils are also stationary, no magnetic field will be produced. Sorry, no EMF will be induced. Okay, so in order to provide time variation between magnetic field and coil, okay, let me rotate this magnet. Okay, here we are rotating magnet. Okay, instead of rotating coils, here we are rotating magnet. Okay, so rotating magnet is called rotor. Okay, here we are rotating magnetic field. Okay, coils are stationary winding called stationary, so called stator. Okay, three separate windings or coils with terminals A dash, B dash, and C dash are physically displaced 120 degrees apart from each other. Okay, when three coils are 120 degrees displaced by angle 120 degrees physically, obviously we are going to produce three voltage which are displaced by angle 120 degrees electrically. Okay, likewise. Okay, likewise we produce voltage. Okay, this is the voltage produced by coil A. This is the voltage produced by coil B. This is the voltage produced by coil C. Okay, all voltages are displaced by an angle 120 degrees from each other. Okay, this is the voltage which is produced by coil A. This is the voltage which is produced by coil B. This is the voltage which is produced by coil C. Okay, all voltages are displaced by an angle 120 degrees from each other. Okay, so if the voltage which is produced by coil A is E1 is equal to Em sin omega t, okay, then the voltage which is produced by coil B would be Em sin of omega t minus 120 degrees. As they are displaced by an angle 120 degrees physically, obviously they produce voltage by taking, by having displacement of 120 degrees from each other electrically. Okay, so E1 is equal to Em sin omega t, E2 is equal to Em sin of omega t minus 100 degrees, E3 is equal to, or E3 is equal to Em sin of omega t minus 240 degrees. Okay. Yeah, we have two types of connections. Okay, normally see, we have in three-phase system, we have three phases or three armature windings. We can also make such kind of arrangement like this. Okay, three phases can be connected to connected separately to separate loads like this. Okay. 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 If a separate load is connected across each winding, okay, as shown in figure here, see, in figure 3 it is shown like this, right? Okay, three phases are connected to loads separately. Okay, we require 6 connectors. Okay, connector 1, connector 2, 3, 4, 5, 6. Okay, so in order to make this kind of arrangement, we require 6 connectors. Okay, so this will make the whole system complicated and expensive. Okay, this will make the whole system complicated and expensive. Okay, so instead of making, yeah, instead of making such kind of arrangement, it is better to have two connections like this. Okay, anyhow, we require 6 connectors to make this kind of arrangement. See, if a separate load is connected across each winding, as shown in the figure, it is difficult to have such kind of arrangement. Okay, and we need to have 6 connectors are required to transmit power. Okay, so instead of having this kind of arrangement, let me have 2 connections. Okay, one is star connected system and the other one is delta connected system. Okay, this is star connection, whereas this is delta connection. Okay, anyhow, here see, this is phase A, phase 1. Phase 1 is having two ends. Okay, start and finish, and this is also having start and finish, and this is also having start and finish. Okay, 3 coils are having 2 ends. Okay, A dash, B dash, C dash. Okay, in order to make this kind of arrangement, that is star connected system or star connection. Okay, what we do is we do one thing. You connect all A dash, all A dash, B dash, and C dash together. Okay, if we connect similar ends means connecting similar ends together. Connecting. I'm facing problem with my cursor. Yeah. Okay. Yeah. We have see, this phase is having 2 ends, this phase is having 2 ends, this phase is also having 2 ends, A dash, B dash, and C dash. Okay, in order to make this kind of arrangement, that is star connection, to connect all similar ends. All similar ends means you connect A dash, B dash, C dash together. Okay, this is A dash. Okay, this is B dash. Sorry, this is C dash. This is B dash. Okay, let me write here. Okay, yeah. This is A dash. This is C dash. This is B dash. Okay, all similar ends are connected together to make this kind of arrangement. Okay, if all similar ends are connected like this, then we can have star connection. You can have star connection. Okay, now here see, coming to this delta connection. Okay, this is A dash, then this will be B dash, then this will be C dash. Okay, see, these two are C dash A, or these two are dissimilar ends. C B dash, these two are also dissimilar ends. A dash B, these two are also dissimilar ends. Okay, so by connecting two dissimilar ends, all dissimilar ends connected together, okay, will form delta connection. we form delta connection. Okay, so if all similar ends means you can also connect like this. A, B, C connected. If A, B, C ends are connected together, that will also form star connection. Okay, so here advantage of this star connection is here neutral wire. This is neutral point. The junction, this junction is called neutral point. This junction is called neutral point. Okay, you can also connect one more wire. That wire is called neutral wire. Okay, so if we connect neutral wire here, you can collect single phase voltage. You can collect single phase voltage from this three-phase system. Okay. Now here see, this is the voltage which is produced by phase A. This is the voltage which is produced by phase B. This is the voltage which is produced by phase C. And we have neutral point. This junction is called neutral point. Okay. Here you can also have neutral wire. Okay. This is delta connection. In delta connection, this is the voltage which is produced by phase A. This is the voltage which is produced by phase B. This is the voltage which is produced by phase C. Okay. Here see, this is N. This junction point is called N. Okay. This is line. This is line. This is line R. This is line Y. This is line B. Okay. We have three lines. Three lines. Again here also we have three lines. This is line R. This is line Y. This is line B. Okay. So the voltage between line to line is called line voltage. The voltage between line to line is called line voltage. Okay, this is line voltage. This is, you can say, VRY. Okay, the voltage between line to line is called line voltage. Okay, the voltage between line to neutral. This is VRN. VRN. This is called phase voltage. This is neutral point N. Neutral point N. Okay. The voltage between line to neutral is called phase voltage. The voltage between line to line is called line voltage. Okay. From this star connected system, you can collect phase voltage from this. Okay. You can collect phase voltage from this star connected system. Okay. Whereas here, line voltage is different as well as phase voltage is different. Okay, coming to delta connection, the voltage between line to line, is called line voltage, that is VRY. This is line voltage, VRY. You can also have line voltage like this. The voltage between these two is also called as line voltage, which is VYB. You can also have the voltage between these two lines. This is VBR. The voltage between these two lines is called VBR. Okay, but here the voltage across this phase is phase voltage. The voltage across this phase is also phase voltage. The voltage across this phase is also phase voltage. That is here, in case of delta connection, phase voltage is equal to line voltage. Whereas in case of star connection, phase voltage is different than line voltage. Okay, voltage across this phase is phase voltage. Voltage between these two lines is also called line voltage, but the phase voltage is equal to line voltage, because the phase voltage is nothing but voltage between this point, and this point. The voltage between this point and this point is called, means the voltage across this phase is called phase voltage. The voltage between line to line is called line voltage. Both are equal in case of delta connection, whereas in case of star connection, these two are different. As neutral point is available here, this is neutral point. This is neutral point. Neutral point. Okay, you can also have neutral wire. You can also connect one wire. If it is unbalanced system, okay, if you connect neutral wire, current will be flowing to this wire. If it is balanced system, anyhow current flowing to this could be zero. Okay, this neutral wire could be zero. Okay, so the voltage between line to neutral is called phase voltage. The voltage between line to line is called line voltage. This is what phase voltage. This is what phase voltage only. VCN is phase voltage. VBN is also phase voltage. Voltage which is measured between these 2 points. Okay, voltage at this point with respect to this point is VBN. The voltage at this point with respect to this point is VAN. Okay, the voltage at this point with respect to this point would be VAB. We can also have naming convention, not only ABC like that. You can also have RLP. Okay, practically we follow this naming convention RYB. RYB. Okay, outside if you see R phase is in red in color. Okay, phase R is red in color. Phase Y is yellow in color. Okay, phase B is blue in color. Okay, practically we are having three phases. Okay, outside we can see three phases. They are in different colors. Okay, they are having different colors. Okay, phase A. You can also have name conventions like this ABC. ABC. Practically we have name conventions like this R by B. Okay, because phase R is red in color, phase Y is yellow in color, phase B is blue in color. Okay, now VAN is phase voltage, VBN is also phase voltage, VCN is phase voltage. Okay, if we add all phase voltage, okay, all instantaneous voltage. Okay, remember one thing. VAN is equal to VM sin omega t is instantaneous voltage. Instantaneous voltage. Okay, so this is VM sin omega t. This is VM sin of omega t minus 120 degrees. This is VM sin of omega t minus 240 degrees. Okay, if we add all voltage, that will be equal to 0. Okay, here in case of balanced three-phase system, okay, all phase voltages are equal. All phase voltages are equal in magnitude, but having different phase angles. Okay, mod VAN means magnitude of VAN. Mod VBN means magnitude of VBN. Mod BCN means magnitude of BCN. Okay, all are equal in magnitude. All are equal in magnitude, but there is phase difference of 120 degrees from each other. Okay, that is VAN is equal to V at an angle 0 degrees means VBN is equal to V at an angle minus 120 degrees. VCN is equal to V at an angle minus 240 degrees. Okay, so here see, phase A will produce EM sin omega t, phase B will produce EM sin of omega t minus 120 degrees, phase C will produce EM sin of omega t minus 240 degrees. Okay, all are instantaneous voltage. Okay, so here it can be proved in many ways that sum of three EMFs at every instant is equal to 0. Okay, so EA, EB, EC. Okay, EA is EM sin omega t, EB is EM sin of omega t minus 120 degrees, EC is EM sin of omega t minus 240 degrees. Sum of all voltage will be equal to 0. You can also have this in polar form. VM at an angle 0 degrees plus VM. Otherwise, you can also have RMS value. VM at an angle minus 120 degrees. Okay, plus VM at an angle 240 degrees. Okay, so here VM into 1 at an angle 0 degrees means 1. Okay, means 1 plus okay, coming to this, what see, VM at an angle minus 100 degrees means what will be this 1 at an angle minus, what is 1 at an angle minus 100 degrees? That is minus 0.5 minus J 0.866. Okay, then 1 at an angle minus 100 degrees. What is 1 at an angle minus 100 degrees? Okay, that will be minus 0.5 plus J 0.866. Okay, if you add all these, then that would be 0. Okay. So it can be proved in many ways that sum of three EMFs at any instant is equal to 0. Okay, coming to phase sequence. Okay, so phase sequence, the order in which voltage in the three phases reach their maximum positive values is called the phase sequence or phase order. Okay, phase sequence is the order in which voltage in the three phases, in all three phases, reach their maximum values. Reach their maximum values is called phase sequence. I'll make it clear. Okay, this is phase sequence, right? Okay, so you can also have definition like this. Okay, yeah, we have two phase sequences. One is ABC sequence. Second one is ACB. See, you can also have naming conventions like this: RYB, RYB phase sequence. Okay, see, this is R, this is B, Y. You can also have phase sequence, naming convention like this. Okay, ABC phase sequence. Okay, or positive sequence. Okay, this is ACB, negative sequence. Okay, ACB sequence. Okay, so now see, yeah, we can read out this. It is important in three-phase power distribution because they determine the direction of. Okay, I'll come back to this point. Okay, now here see, coming to phase sequence. What is mean by phase sequence? The order in which voltage in the three phases reach their maximum positive voltage is called phase sequence. Okay, so where is my cursor? Yeah, yeah. ABC phase sequence. Okay, according to definition, the order in which voltage, the order in which, the order in which voltage in all phases reach their maximum values. Order of reaching maximum values. Okay, simply speaking, order of reaching maximum values is called phase sequence. Okay, so here see, first phase A is reaching its maximum value. Okay, uh, phase voltage produced by phase B is reaching maximum value next. Okay, then phase C. Okay, phase A is reaching its maximum value first. Next phase B, then phase C. Okay, so phase A reaching its maximum value first. Okay, then phase B, then phase C. Okay, so the phase sequence is A, B, C. Okay, so here you know, right? See, this is your rotating magnetic field. Your rotating magnetic field. Here we have coils in case of three-phase generator. Okay, so here your rotating magnetic field, right? Okay, so let me rotate this rotor in anti-clockwise direction. If I rotate this rotor in anti-clockwise direction, okay, so first A attains more positive voltage. Okay, then B attains more positive voltage. Then phase C attains more positive voltage. If you rotate this rotor in anti-clockwise direction, phase A attains more positive voltage first, then phase B attains more positive voltage, then phase C attains more positive voltage. Okay, that's why the phase sequence is A, B, C. Okay, it is the order of reaching their maximum values. It's called phase sequence. Okay, so the phase sequence of this is A, B, C. Okay, first phase A is reaching its maximum value, then phase B, then phase C. Okay, so we can have you know, right? EA is equal to what? EA is equal to EA is equal to EM sin omega t, right? EM sin omega t, which is equal to, you say, E at an angle 0 degrees, B at an angle 0 degrees. Okay, so let me have phasor like this. This is E A, E A, this is E A, B at an angle 0 degrees. Okay, coming to EB, EB is what? EB is equal to EM sin of omega t minus 120 degrees or B at an angle minus 120 degrees. Okay, that is this voltage EB lag EA by an angle 120 degrees. So we can have phasor phase voltage, we can have phasor like this. Okay, this is what? This is EB. EB lags EA by an angle 120 degrees. 120 degrees. let me draw phasor EC. Okay, EC is what? EC is B at an angle minus 240 degrees. Minus 240 degrees means what is the phase displacement between EB and EC? EB and EC 120 degrees. Okay, so EC is EC lags EB. This EC lags EC. EC lags EB by an angle 120 degrees. So we can draw EC like this. Okay, the angle between these two is 120 degrees. Okay. The angle between these two is also 120 degrees. So you can have, right? Okay. So V at an angle 0 degrees, V at an angle minus 120 degrees, V at an angle minus 240 degrees. Okay, you can also have V at an angle plus 220 degrees. See, this is reference axis. This is reference axis. This is reference axis. This is reference axis. Okay, V at an angle 0 degrees. You can draw VAN like this. This is phasor VAN. Okay, next VP is VP at an angle minus 120 degrees. So you can have phasor like this. Okay, the phase displacement is 120 degrees. Okay, next we can have VCN like this. Okay, VCN lags VBN by an angle 120 degrees. Okay, so the angle between these two is also 120 degrees. Okay, now here see VCN lags VBN by an angle 120 degrees. The angle between these two is 120 degrees. Okay, so now we can also say like this: VCN leads VAN by an angle 120 degrees. VCN leads VAN by an angle 120 degrees. That's why it is written like this: VP at an angle plus 120 degrees. This is also right. Okay, because this VCN leads VAN by an angle 120 degrees from phasor diagram. Okay, now coming to negative sequence. Negative sequence. So what we do is instead of rotating this, see, we have rotated this in counterclockwise direction earlier in order to have what phase sequence ABC. Right? So let me rotate this rotor in clockwise direction. In clockwise direction. Okay. If I rotate this rotor in clockwise direction, if I rotate this rotor in clockwise direction, okay, sorry. If I rotate this rotor in clockwise direction, okay, which phase will attain positive voltage first? Okay, phase A will attain positive voltage first. Okay, then phase C, then phase B. Means this would be phase A only. This would be phase C. Sorry, this is phase C. Okay, this will be phase B. Okay, so if I rotate, instead of rotating this rotor in anti-clockwise direction, let me rotate this rotor in clockwise direction. If I rotate this rotor in clockwise direction, phase A attains more positive voltage, then phase C, then phase B. Okay, so this will be ACB. Okay, the phase sequence is ACB, negative sequence. Okay, so here now, what is the observation here? Okay, now here the phase sequence is ABC. Okay, here the phase sequence is ACB. Okay, what is the observation here? Here the rotor is rotating. The rotor is rotated in counterclockwise direction. The phase sequence is ABC. The rotor is rotated in clockwise direction. The phase sequence is ACB. Means if you change phase sequence, I can change the direction of rotor. I can change the direction of rotor by changing the phase sequence. Let me take 10 more minutes. I'll finish up in 10 minutes. So here, you know all these things, right? Okay. So VP at an angle 0 degrees, VP at an angle minus 120 degrees, VP at an angle minus 220 degrees, that is VP at an angle plus 120 degrees, as VCN leads VAN by an angle 120 degrees. rotates in clockwise direction. This direction is in this direction. The rotor is rotating in clockwise direction. The rotor is rotating in clockwise direction. Okay. Phase A attains positive voltage first, then phase C, then phase B. Sorry, here phase A, phase B voltage, and voltage by phase. Phase B. Okay. See, as it is having ACB sequence, negative sequence. In case of ABC sequence, VAN, VBN, VCN. In case of ACB sequence, VAN, VCN, VBN. Okay. First, VAN attains more positive voltage, then VCN. Then phase A attains more positive voltage, phase B attains more positive, then phase C. Phase B. Okay, now coming to problem. Okay. Determine the phase sequence of set of voltages. Okay, so VAN is given like this: 200 cos of omega t plus 10 degrees. VBN is 200 cos of omega t minus 230 degrees. VCN is equal to 200 cos of omega t minus 110 degrees. Okay. So here, what is the phase sequence? This can be written like this: 200 at an angle 10 degrees. Okay. 200 at an angle 2 minus yeah, 200 at an angle minus 230 degrees, 200 at an angle minus 110 degrees. Okay, so here phase A attains more positive voltage first. Okay, so let me add, see, anyhow, the phase angle between all voltages is 100 degrees. All voltages are displaced by an angle 120 degrees from each other. Okay, so let see, this is 200 at angle 10 degrees means what will be next voltage? Next phase voltage would be 200 at an angle 10 degrees minus 120 degrees. Okay, so if I add minus 120 degrees to this, okay, let me add minus 120 degrees to this. If I add minus 120 degrees, what will you get? 200 at an angle minus 210 degrees. You are getting 200 at an angle minus 210 degrees, sorry, 110 degrees. 110 degrees means what will be next voltage? Which phase will attain more positive voltage? Okay, next to VAN, VCN. Okay, now you add minus 120 degrees to this. Okay, then you will get this voltage 200 angle minus 230 degrees. 230 degrees means phase A attains more positive voltage first, then phase C, then phase B. Okay, so the phase sequence is ACB, negative sequence. Phase sequence is ACB. Now, coming to this column, last column, given that VBN is equal to 220 degrees, 220 at an angle 30 degrees volts, find VAN, VCN, assuming a positive sequence, positive phase sequence. Okay, positive sequence means, okay, positive. What is positive phase sequence? Okay, phase A attains more positive voltage first, then phase B, then phase C, right? Okay, so if phase B is given like this: 220 at an angle 30 degrees, 30 degrees means anyhow this will lead, this voltage leads this voltage by an angle 120 degrees. See, meaning of, see, phase B lags phase A by an angle 120 degrees, or phase B leads phase A leads phase B by an angle 120 degrees. So you add 120 degrees to this, then this would be 220 at an angle 30 plus 120. Okay, now coming to this. Phase C lags phase B by an angle 120 degrees. So 220 at an angle 30 degrees minus 120 degrees, which is equal to 220 at an angle minus 90 degrees. Okay, let me wind up this session. More time. So